Okay, thanks a lot for coming back. I hope you survive the heat, but we'll see. Okay, let me recall where we left. There was a proposition saying that if you have any algebraic group which acts faithfully and rationally on the variety x, and if x is rational, or actually rationally connected, then G is linear. Okay, so let me try to prove this, even if, as you see, I'm not too happy with this proof. So, first of all, we saw last thing this morning that you have an exact sequence like this. This is a connected component of G. It's enough to show that G0 is linear. For example, because linear is the same as affine, and affine is the same for G and G0, because G is just a union of finite many copies of G0. Okay, so we will do this, and we'll try to show that this abelian part is trivial. Okay, so we had some information on this variety X from the proof, or starting point of the proof of this Weil's regularization theorem. We had a quotient and we had a generic fiber which is homogeneous under the group obtained from G by base change, where L is a function field of Y, which was a field of G invariant functions on X. Okay, so that's where we are. And what I will claim there exists a dominant rational map of L varieties F from this L variety Z to the base change AL. A is this one. Okay? So how this claim implies the proposition. By some small trick, because you look at the function field of this by this construction, we have K of X as a L field. This is L of Z, right? Okay, so we have to play with fields over K and L in this business, and to be a bit careful. And then, as an L field, L of Z contains L of AL by the inverse homomorphism of this. But if you think about this, L of AL is K of Y of the base change of A to K of Y. So this is just K of Y times A. Okay. So if you're not happy with this, you just think about it. I think it's a small trick. And now you see that this corresponds to a rational map. In the other direction from X to okay, and now this is really over K. And then you see if X is rational, you cannot send a rational variety to a abelian variety. Maybe I'll put it as an exercise, even if we already saw this. Every homomorphism, well, maybe a rational map from E1 to A is constants. This occurred in earlier talks that abelian varieties have no rational map at all. So you see, if X is rational, it cannot project to A. Yes, rationally connected is the same. All the rational curves in X are contracted in A, and so there is no way. So that's how this claim implies the proposition. Now let me try to prove the claim. Well, we have a homogeneous variety Z under G lin, and we will have a second claim. Sorry, this is I should number these claims. Well, the second claim is that Z mod G lin is quotient. In the sense of categorical quotient, you have a variety with L action, G L action. You take the quotient by this subgroup. But first of all, it exists, and is a torsor under a finite quotient of what remains. So what remains is you just do G lin mod G lin L, and what you get AL. Okay, so AL is a L abelian variety, and the claim this exists, and it's a AL modulo something torsor. This is something we don't control, as we will see in the proof. So, sorry, this is just to keep you and me awake during the afternoon. I just prove things in a completely scary way, but anyway. Okay, so the good thing with this claim is it's unchanged by field extensions. Maybe you don't only need finite Galois. Meaning if it holds for L, it holds for any bigger field, just base change. And conversely, if it holds for a finite Galois extension of L, you can use this Galois descent machinery to come back here. Doesn't change the existence of quotients because you just make the quotient by the Galois group. And being torsor is invariant under any kind of faithfully flat base change, right? So you can do this. And why I'm observing this? Because after some finite extension, you may assume that your variety has an endpoint. Well, maybe I'll work officially over some L prime. So you may assume D has an L point. After going to this L prime. And now, well, you know that Z is a quotient of GL by some subgroup. Because it's a homogeneous variety. You just write it in, as a homogeneous space, H. And H is, of course, the stabilizer of some point. But now, the action of GL on Z is faithful because the action of G on X was faithful from the start. So GL acts on Z faithfully. And this morning I stated a kind of lemma which says that the isotropic group in this situation is linear. Okay, and the proof was just if you have a algebraic group action, which a point, then the stabilizer of this point is linear if the action is faithful. So this general fact. Now we just I'll use it. And we consider the exact sequence from Chevalier's theorem, but for L, just base change. And this H is somewhere here. And now there is this neutral component, H naught, okay, which is a connected linear algebraic group. And I claim this H naught is here. And the proof is instant because if you send it to AL, it doesn't survive because it's connected, affine, and abelian variety. So you have this H naught here, and hence, if you look at this quotient, GZ mod G lin L, now, well, this G lin acts on the left on this, and if you take the quotient by G lin, take this, and it's just GL modulo G lin L H. This is a subgroup generated by both. This was in his normal subgroup, so there is no big problem in this. And first of all, you use this. So you have only to consider AL modulo the image of H mod H0 is the image of H in this quotient. And this is, of course, a finite group because this one is finite. So you see that after some field extension that I wrote implicitly, you get a honest abelian variety. And this tells you that before that, it was a torsor. Because you still have the AL action on this. And after some base change, it's just a torsor with a finite group. And now what you do, is, well, this proves claim 2. And now I have to use a result of Serre on abelian torsors. So you see this abelian torsors occurred in earlier talk by Evgeny, when you saw that they are parameterized by some Galois cohomology group. Okay, just abstract nonsense. But this result of Serre says that this group is torsion. So this is a commutative group. You have a natural operation on torsors under this abelian group, and this group is torsion. And in concrete terms, reformulation is that there exists a map from Z mod G lin L, which is the total space of our torsor, to some kind of stupid torsor over A, under AL. Quotient of AL by some finite group. This is a torsor with a k-rational point. Well, it implies that every torsor has a reduction of structure group to the group of n torsion of the abelian variety. And that's more or less what you see. Okay. If you want an idea of a proof, you can do the following. I will just wave hands. First of all, if you have a trivial torsor, then you just take AL mod F, right? If you have a non-trivial torsor, you trivialize it after a finite-based extension. And on the top space, you have an action of the Galois group. And then you can take the kind of barycenter of points, sum of points. This is an operation which is invariant under the Galois group and which produces a map to an abelian variety. And that's the proof. You can also look at this in a book by Milne on algebraic groups. This idea is worked out in a very nice way. Okay, but anyway, that works. And why does this complete the proof? Because you see every finite group of an abelian variety is contained in some n torsion group for some n. Okay, so you this is just the trivial fact that every finite commutative group is killed by some integer, right? And the good thing with this group is this is A of n L. Okay. Commute with base change. And so what you get, actually a surjective morphism. From Z to AL modulo A of n L. But this is A. And the map is just multiplication by n. Right. This goes the other way around. Take x to nx from A to or AL to itself. It has kernel exactly this, and so it gives you this isomorphism. Yes? Yes? But well, maybe I'm waving too much my hands. If you have an L point, you get this. And in general, yes. So let's complete the argument if you have a L point. And then I say too quickly that this gives a general case. Okay? Okay, so, well, that's a proof of the claim 2, which in turn implies the proof of claim 1 and the proposition. And again, if you find a proof which is more direct, it will be very welcome in this topic, because we feel there is no need to go to abelian varieties to prove that such a group is linear. So this is supposed to give you a proof sketch of Weil's regularization theorem for rational varieties. In particular, it applies to the Cremona group. And in general, you need more use of Chevalet's theorem, structure theorem to complete the proof. And as this is quite technical, I will not go into that. I will rather try to do some addition to this regularization theorem. So addition. So now I will take G linear and acts rationally and faithfully on some variety X. Then the claim is there exists a projective variety Y together with birational isomorphism so the rest is the rest of the statement of Chevalet's of Weil's theorem and G action B on Y, which regularize the original action. So you have this commutative diagram that I recall. Okay, so the additional word is projective, and then you can even add smooth. Because of what we discussed on equivariant resolution of singularities. Once you have a projective variety, you can make it smooth by resolving singularities in a canonical way, and group actions automatically lift to this canonical resolution. So at the end, we get this model. And again, the assumptions are K algebraically closed, and for this part of the proof, it's absolutely crucial to have characteristic 0, because again, equivariant resolution is not known. So let me explain how you prove this, how you can add this word projective. So this will be extremely sketchy, because well, I was very badly organized and I spent most of my time on, well, in the beginning. Okay, and first of all, if you look at the proof, you may assume this variety Y, which occurs here, to be quasi-projective. And this goes by inspecting the proof, because at the very end of the proof, we constructed this y. Sorry for the notation, which was, maybe I should call it, sorry. I don't know where to change notation, but let me try something. It was contained in some Pn times another y prime, for some y prime we thought was affine. And we took the closure of some intermediate varieties there. So it's clearly quasi-projective. And of course, you may assume smooth, because you can always make varieties smaller by this, as long as they are stable by the group action. Just take the smooth points. And then in the mathematical literature, there are two papers by a Japanese mathematician called Sumihiro, which are called equivariant completion. They are not new. They go back to this years, and they do exactly what we need. So let me comment on this problem. Okay, so I'll do some general comments. You start with an abstract variety, y, and you know that you can embed it in a complete variety as a dense open. This is called Nagata's completion theorem, and it's a very important result. Even in practice, if you have y quasi-projective, you don't have to bother. You just embed it in a projective space and close. Okay? So again, given y, there exists y bar having this property. And this is Nagata. And it's an open question how to do it equivariantly. Well, it's an extremely basic question. For finite groups, it's easy, because you take the product of conjugates or whatever. For connected groups, it's wide open. And this paper solves this problem for G linear and X, well, maybe. So G linear will assume for X normal. And in particular, Sumihiro proves that if G is connected, let me pose what's the complete assumption, unconnected, and X is normal, then and quasi-projective, which is almost our case, except a connected assumption, then what we can find is an embedding of Pn where G acts linearly. So there is, as in this morning, you have immersion and a representation which are compatible. And then you just take the image and close, and you get your completion. So how does this work? There are a number of constructions from group actions, which I will only sketch because by lack of time, but are kind of interesting in their own right. Well, first of all these varieties are not projective, otherwise there are no problems. So one has to be careful if you have experience and intuition from a projective setting, things will be a bit different. For example, spaces of sections of line bundles are usually infinite dimensional. Okay, so you have to be a bit pull down a little bit. And the first thing is to understand morphisms to projective space in an intrinsic way, together with a group action. And you know very well how to describe morphisms from X to projective space. This is the same as, well, maybe F. First of all, a line bundle, L on X, together with global sections which have no common zeros. Okay, that's a thing you learn when you well, learn about the projective space, and can be found in Hartshorne's book, chapter 2. Okay. And the correspondence is to F, you associate, of course, F star OPN1, and the pullbacks of the coordinates. Homogeneous coordinate functions give you sections of this, you just take their pullbacks. Okay. So the first thing is to get some more intrinsic or coordinate-free version of this. And this is a very classical topic, which is called a linear series. So this goes as follows. I just replace Pn with a projectivization of a vector space. So I forget about coordinates. And this will be the Grothendieck convention, the projective space of hyperplanes. And this corresponds to some line bundle, L, together with a map, phi, from this space V to the space of global sections with base point free image. Okay, and the correspondence is the same. The line bundle is a pullback of O of 1, and this V gives you sections of O of 1, which is Grothendieck convention, and I take pullback of this. Okay, so that's just a reformulation, but it brings us a bit closer to our aim, which is to understand this equivariant morphisms to the projective space for some action. So in this approach, well, you have to, again, to guess or adapt all these ingredients to an equivalent setting. And part of it is easy to guess. For this, we need V to be a representation of G. You have your group G. Okay, but then you have to do something with the line bundle, and the definition, relevant definition, is a notion of linearization. Where G is an algebraic group, and X is a G variety. Well, this is something you have probably seen or heard about from geometric invariant theory, because it's a basic object you work with. This is a G action in the sense of action of algebraic groups on the total space of L, such that pi is G equivariant, and the action is somehow linear. Linear doesn't mean anything in this setting. It would mean it sends a fiber, which is a line, together with its line structure to another fiber, and the induced map is linear. So the G sends Lx to Lgx linearly. And this is, well, maybe less intuitive but equally correct reformulation. It's to say that the G action commutes with the GM action on L, just by scalar multiplication on fibers. You have a line bundle, you can do this scalar multiplication. Okay. And then there are two easy facts. Yes, I think so. Yes. Yes. Right. But, well, I feel this one is more intuitive. This one is what it is, but this one is more intuitive. But then there are two kind of basic facts when you have a G linearized line bundle. Let me insist. You have your line bundle. A G linearization is an additional data. It doesn't come with the bundle. And in general, it's not unique. But if you have a G linearization, then you get a representation of G on each space of sections, of powers. Maybe gamma, X, L, maybe Z. And how do you see this? Well, G acts on the ring of regular functions on L, and it decomposes into homogeneous pieces according to the GM action. And these homogeneous pieces are exactly these spaces for maybe n positive. To get n arbitrary, you just remove the zero section and do the same. Okay. So you have this, and as I mentioned, this could be infinite dimensional. But when you read G representation, this should be union of finite dimensional algebraic representations. Okay, so you in this big vector space, you have a collection of subspaces which are G-stable, and on which G acts by a homomorphism of groups to the corresponding GL. So that's the definition of representations. And the second fact is that well, you have a complete analog of linear series that equivariant morphisms from X, this G variety over there, to some P of V, where V is a finite dimensional G representation. They correspond bijectively to the pairs, well, like over there, L phi, where L is G linearized, and phi is an equivariant morphism. Of the representations. Okay, so you put the G at appropriate places, but the main one is this G linearized business. Okay, yes? Yes? Mm-hmm. Well, it's just you can act on a trivial bundle by scalar multiplication on each fiber via a character. And these are all the linearizations, because they differ by invertible functions, which are constant. Okay, so you get this. Okay, so that's maybe what you need to know about these things. And now comes a result of Sumihiro, which says that most line bundles have some G linearization in loose words. So this precise statement is as follows. You have a G which is a connected linear algebraic group, and X is a normal variety. L over X is a line bundle. Then some positive power has a G linearization. For some n, which only depends on G, and which is a positive integer. Okay? So that's the main technical ingredient of this proof that I'm sketch. And the corollary of this is the following. If X is quasi-projective, well, sorry, I forgot something here, which is the image is base point free. To get this correct, then X embeds G equivalently for some finite dimensional G representation V. Okay, so and this is what we wanted. So how does this follow? Well, you can put all these small pieces together, basically. So first of all, X being quasi-projective has some ample line bundle. Maybe very ample. This, by definition, this exists. We can replace it with some positive power to get it G linearized. Okay, by this result, then you pick up some subspace of the global sections of L, such that the corresponding rational map is embedding. This exists because you have a very ample line bundle. And since you have a G module structure here, and this V is, of course, finite dimensional, you can put it in some intermediate finite dimensional W. Okay, just make it G-stable by choosing a basis and putting each basis in a G module, making the sum. And now the claim is actually with this business, you have a map like this. This is covariant, I know. And then X embed also in this space, right? By just common sense. And now this embedding is equivariant. Because you generate your line bundle by the sections of B vector space. Okay, so that's the proof. And you see the substantial work is there. Maybe in the remaining 12 minutes, I won't give you an idea of the proof of this. I'd better well, anyway, this is not too easy to get out of the original papers, and there are modern expositions of Sumihiro's work, for example, by myself or whatever, which is hopefully accessible. So I'll just leave this like this, and I want to go back to surfaces, because in the first lecture, I tried to present another theorem of Castelnuovo. No, that was Enriques, sorry. Confused with these Italians. The theorems of Enriques said that all the connected maximal algebraic subgroups of Cremona 2 were connected automorphism groups of rational surfaces, rational ruled surfaces that we know very well now. And I want to explain how do you get back this theorem. So let me restate it, hopefully correctly. And Jeremy will correct me if. First of all is a request, hopefully. Okay, so every connected algebraic subgroup of La 2 is contained in the maximal one. That's the first point. And every connected maximal algebraic subgroup of Cremona 2 is either haute E2, which is EGL3, haute Fn, and we saw its structure in Jeremy's talk, for n bigger than 2, or haute 0 of F0, which is PGL2 times PGL2. Okay, and that was the statement. So finally, we should be able to get this. Okay, so how does this work? So you consider your group G. And using Weil's regularization theorem, you put it in the automorphism group of S for some projective rational surface. Okay, that's what we sketched. Now, well, you can put a 0 here because your group is connected, so no problem. And now we have a kind of minimal model, which is either P2 or Fn. And this morphism is a sequence of blowing ups of points, right? And this is an example of a contraction in the sense of, I guess, lecture 2, proper morphism, such that the direct image of structure sheaf is a structure sheaf. Anyway, you don't have to check it because the target is smooth. And then you have Blanchard's lemma, which tells you that root 0 of S is mapped to root 0 of P2 or Fn by some induced homomorphism, because Blanchard's lemma tells you that this group acts in a unique way on these surfaces so that the morphism F is equivariant. So I reformulate it in this way. And since this map here is birational, you don't change anything on an open subset, this is has trivial kernel. Okay? So in characteristic 0, you get inclusion of algebraic groups. So in conclusion, G is contained in this, which is contained in this one. And that's a proof. Okay. Well, I was really fancy because I used a very big tool, which is, yes? Which one? I guess so, yes. Ah. Yes, yes. Yes, you're right. I didn't prove this part. You're completely right, and I think I won't do it. Because, well, actually, it becomes an exercise in group theory, because, for example, out Fn cannot be embedded in out Fm for another m by looking at the translation part. This translation part, you remember, this is a homogeneous polynomial of degree n in 2 variables as a representation of GL2. And this is irreducible. So it has nothing to do with other ones. Okay? And for even more stupid reason, you cannot embed this root Fn in PGL3. okay, or backwards. So these groups are pairwise. Well, luckily for me, okay, they are pairwise, not comparable. Okay, so that's you're perfectly right. So, well, I should say that, as usual in this course, I used a very big tool to prove this, which is canonical desingularization of surfaces. Because this is hidden in the word smooth. Actually, we more or less got a complete proof of projective. But then I told you there is this canonical resolution. And for surfaces, there is one which is quite nice and worth knowing, which is Zariski canonical resolution of surfaces. Well, you start with a possibly singular surface, S0. You go to the normalization. I denoted with a prime in earlier lecture. So this is a normalization. Then you blow up this S prime 0 along the singular locus. Which is a finite set of points because you have a normal surface. It's only singular in codimension 2. So, and I intentionally write singular locus because I want to blow up all points simultaneously as distinct points, right? And then you start again. This will be my S1. Then you normalize, and then you blow up the singular locus. And you iterate this process. And Zariski's theorem tells you this stops. And when it stops, your surface is smooth because first of all it's normal, and secondly there is nothing to blow up. Okay. And now you remember we discussed some formal considerations in lecture 2 about functorial behavior of group actions. So they lift to normalization and they lift to blow up of globally invariant closed subsets. And so this process, in this process, all algebraic group actions lift automatically. For the blow up, the group action may permute the singular points, but you don't care, you blow up simultaneously. So at the end, you obtain a surface with an action of your favorite algebraic group coming from S. Well, now comes something which is not too clear to me. Because, okay, you get this Zariski resolution, and you have also minimal resolution. And because it's minimal, these factors, so some, these are sequence of blow-ups of points. And usually, these things differ. The Zariski resolution might be larger. But then, using again Blanchard's lemma and a little bit of thinking, we see that every algebraic group action on S0 lift uniquely to S min. And this I don't know how to prove directly because it's a very simple statement, right? Because this S min, you don't, well, it's not clear to me what it does exactly. So, but again, well, the way to see it, you lift to S and you contract all -1 curves, which are contracted here or whatever. So you contract a set of -1 curves which is permuted by the group. And you apply Blanchard's lemma for the connected part, and for the non-connected part, you have a small argument. So this is some question. Maybe someone in the audience has an answer to this. And well, thank you for your patience. Answers? Yes? Yes? Oh, well, that's sorry. Sorry to insist that that's a permanent problem with algebraic group actions. Even if you lift the closed points individually as automorphisms, at the end you get a honest group action, which is a morphism from G times or homomorphism to the algebraic group. This construction only produces homomorphism of abstract groups to the algebraic group. Well, probably, but this requires an additional argument. And I'm always stuck with these arguments unless I can use some machine. Okay. Yes, yes. Mm-hmm. Yeah. Contractions, yes, for the connected part. Flips, you have to think because you have to see that the operations are intrinsic. For example, if you use relative canonical bundles to do flips, then you're in good shape because these are certainly linearized, right? Okay. So I think that's hopefully that answers, but you have to be a bit careful if you do random flops. Okay. Sure. Mm-hmm. First, if G is linear, there are very few linearized bundles. For example, on an abelian variety, you only get the trivial bundle. And this is morally correct because you cannot put an abelian variety equivariantly in a projective space. You have no abelian variety action on the projective space. Okay. So, but you have some substitutes that I cooked up in my paper on models of algebraic group actions, which are really heavy-handed. So you need some Weil restriction process. Actually, you start with a linear part. You embed your variety, complete it equivalently for the linear part. And then there is a kind of co-induction process which uses sections of associative vector bundles. Okay, so of associated bundles. So I can explain to you privately, but I think it holds, but the proof is there is one additional layer. Maybe I can sketch it, but this is a kind of strange construction. So assume you have your X, and you have your G, and you have this G, not G lin, which is A. Okay, you know how to embed it X for G lin. And then what you do is to embed it further in a hom G of G lin of G X bar by some process which is just induction representation theory, exactly the same formula. And then you see this has a natural scheme structure coming from this functor of sections of morphisms, growth index Weil restriction, the one which is really big. And it's not yet projective, but you can embed it in a Hilbert scheme by definition of sections, and this gives you the correct place. So it's a kind of crazy construction. And on this Hilbert scheme, first of all, you have a bounded family, otherwise you're in trouble. And secondly, the Hilbert scheme, every bounded part in the Hilbert scheme is canonically projective. Because each piece embeds canonically in a Grassmannian. So you equivalently with respect to everything. So at the end, you get a construction where I'm not so happy with this business. Okay, so it's a really, well. This proves the whole stuff also for G non-connected. All you need that the quotient is proper. Okay, so yes, yes. Everything is true in positive characteristics. Because first of all, you have this canonical resolution, which is characteristic free. Actually, it works over any field. It was proved by Zariski over algebraically closed fields. And then there is a kind of exposition of Kossar, references in the notes, which does it over any field. And secondly, this Weil regularization works over in arbitrary characteristic, just in a much more technical way, because you have to be careful with group schemes. But that's it. So things work, but for additional price. Sorry. Well, thank you.